much. So let us begin our last talk for today. The whole fest, and the speaker will be Misha Verbitsky, who will talk about Torelli's theorem for hyperkähler. Thank you very much for
work. Oh, it works. For the introduction, and it is of course great to be there on this conference. And when I was choosing the topic, it was a hard call because I wanted to find the area which was most influenced by Blaine, and somehow most of what I did was influenced in some way. And maybe I should have chosen G2, but in the end I decided for hyperkähler. So what is it? Well, you see there's a definition written on the slides, but I will just repeat that. We have manifold M, 3 complex structures satisfying quadratic relations. I times j is minus j times I is equal k. Complex structures, of course, everybody knows that, so structures. Then you have, you can consider this manifold from differential geometric point of view as a manifold with special holonomy, or you can consider it from algebraic geometric point of view as a manifold with symplectic holomorphic structure. There's an equivalence. So this is equivalent in compact case to manifold with which is scalar and holomorphically symplectic. So for algebraic geometric point of view, of course, no, they hate these quaternions, in fact, algebraic geometers, and they try to think of this as a holomorphically symplectic projective manifold. And of course, for differential geometers, this representation is extremely useful. And as you will see, it has much uses in algebraic geometry as well. When I was almost like a school boy, I learned about hyperkähler manifolds. That was extremely fascinated. And then it was before the Besset's book appeared in Russian. It was, I think, only in French. So everybody was telling me to read this book. It was, I think, like 87, and I did it. It was extremely difficult because it was Soviet time. So when you want to get a book in the library, you had to fill a form and then wait for half an hour, and they bring it to you, and you can sit in there and read. It was the first book in English I ever tried to read, and I didn't find any hyperkähler manifolds there. So I was confused, but a couple of years ago I was given a course of lectures in Moscow on the hyperkähler, Kalabiao mostly, and this was the central literature in this course. So in the end, I think I understood what was in this book. So this is a plan for today's talk. I will start with what is it, Teichmüller space? What do we want actually to produce by stating this Torelli theorem? So I will explain just what are the ingredients of that, without telling you what is the answer, just what is the question. Then I will say something about topology of hyperkähler, well, algebraic geometry of calibrations. Of course, this is the central idea which went into this subject. Then a bit about topology, which actually doesn't use much of the calibrated geometry, of course. And then I will just compute 2 of ingredients in the Torelli, which is mapping class group and Teichmüller. So let me give you first, what is it? I mean, the subject of the talk. What is this subject? So what we have now is that we are studying the a moduli space of complex structures. Of course, you can do that from algebraic geometric point of view by looking at the schemes and doing these representable functors. But since, well, it's easier to do this differential geometrically in that subject because the grid index approach is very powerful, but somehow it's hard to explain and hard to work with, especially in complex algebraic geometry. And of course, the whole thing is very much complex. There's some of the key ingredients in the argument are using very much non-algebraic manifolds. So what do we have now? We have the infinite dimensional space of the complex structures. Integrable. You can think of it as a Fréchet manifold. Complex structures. And then you have this other infinite dimensional Fréchet group, which is group of isotopies, which is, of course, diffeomorphisms, which are connected to identity. This is the connected component of diffeomorphisms. And the Teichmüller space is this comp divided by diff 0. This is very well known for Riemannian surfaces for one-dimensional complex manifolds. And this is how the first moduli space were obtained by Teichmüller. To obtain the moduli space, you just take the forward quotient. So you take the Teichmüller by the group of connected components, where gamma is diffeomorphisms. It's better to take plus for some reason here, divided by diff 0. And why this is good? I mean, you can always take the quotient by diff. For Teichmüller, this approach was very useful because this first quotient is finitely dimensional complex variety, which is actually has very simple topology, simply connected. And then he took the quotient by this Teichmüller group. It was called Teichmüller group, I think. In Russia, it's still Teichmüller group, but in English, it's mapping class group, I guess, because Teichmüller was a bad guy. Okay, so we take this quotient. And the interesting thing is that in dimension more than 1, this moduli space is completely nonsensical. I mean, it has so bad topology, you can't work with it. The only thing you know that there is one-to-one correspondence between points in this very non-Hausdorff space and complex structures. So you can answer all interesting questions about complex structures if you know these ingredients. So this is Teichmüller space, and this is mapping class group. And if you can compute this and this, you are done. And this is how, of course, how they did it for the groups. Except that for the groups, the Teichmüller, the mapping class group is very bad. I mean, it is not, I don't think it has even, it's not a matrix group. It doesn't have any reasonable representations. And in our case, the mapping class group is even arithmetic. You understand it almost completely for special case, for known cases of hyperkähler manifolds. So this is what I will be doing now. Except that so this is bad, but this and this is good, and this is how one proves the Torelli. Okay. Please ask questions if there is something unclear. I would be very grateful. Oh, yes. So now I will tell about the use of the calibrated geometry in that, you see this famous paper. It was a paper I was carrying with me for last 10 years almost continuously. And so it was, very much influenced the whole subject, I think. So there is a definition of calibration. It was done yesterday in beautiful talk by Salor, so I want to repeat it much. I hope everybody knows that. But just so you have eta calibration and examples are omega p divided by p factorial, where omega is scalar form. Okay, and looking at this calibration and the corresponding geometric quantities and constructions, you can actually reconstruct a lot of almost the whole algebraic geometry of complex manifolds. And this was the idea which sort of sits behind the corresponding work for hyperkähler. Yeah, but in fact, I suppose you can do that with the whole Berger table. So you have this table. I hope everybody have seen that a lot. But the table where, if you have a Riemannian manifold, it can be decomposed on product of some general Riemannian manifold and some special Riemannian manifolds and some locally symmetric spaces. And this special manifolds, they all sort of defined by holonomous, by the calibrations. For each of them, you have a special calibration which sort of determines the geometry. So maybe what I'm telling today about hyperkähler was useful, I hope for that, useful for other geometries. So what is it, this subject of calibrated algebraic geometry? We know that very well for this example, and I can tell you only mostly about the hyperkähler example. I have completely no idea how to work with it in other situations, except that we have some bits of complex analysis, namely the calibrated plurisubharmonic functions, which Harvey was telling us some days ago. And we have subvarieties, which are sort of an answer to the complex analytic subvarieties. And in hyperkähler case, this works. So now we have this hyperkähler manifold. We have on this manifold, so M is hyperkähler. You have three symplectic forms: omega I, omega j, omega k, three symplectic forms. It turns out that by taking some products of these forms, you can find many interesting calibrations. And for today's talk, the most interesting calibration is this hyperkähler calibrations. It calibrates hyperkähler subvarieties. So it's theta p, which is omega I square plus omega j square plus omega k square, divided by some power p, divided by some constant, which doesn't matter much. It's just normalization constant. And the claim that z is calibrated by theta p, if and only if z is, well, hyperkähler. I will explain what it is in the next slide. And then it turns out that these kind of cycles have their own algebraic geometry, and you can work with them almost as, even in some sense, better than in the situation of complex analytic subvarieties. Okay, So now the definition, a subvariety is trianalytic if it is complex analytic with respect to I, j, and k. Well, I probably wouldn't write it, but this is what I meant by hyperkähler in these quotes. And if you have, so the trianalytic subvarieties has many interesting properties. You can resolve singularities. This is one of the important. So if they are singular, these singularities are very simple. They are just intersection of planes, which you can just remove by normalization. Also, if you have a complex deformation of trianalytic subvariety, it remains trianalytic. This is precisely, if you think of calibrations, you will see this argument. I mean, you deform complex subvariety, its volume remains the same because its volume is homology invariant because it's calibrated, but then its volume with respect to this calibration remains the same as well. So it has the same volume with respect to the calibration as its Riemannian volume, and then it is calibrated by this calibration theta. This is why when you deform a trianalytic subvariety, it remains trianalytic, even if you deform them in complex category. But then you have many different complex structures on this moduli space, and this gives you the final statement that the moduli of trianalytic cycles is again a singular hyperkähler variety. And there is an intrinsic definition of singular hyperkähler, which I won't tell you, but you can check that this satisfies this definition. You can remove singularities by blow up, by just normalization, in fact. So this sort of allows to speak of hyperkähler algebraic geometry in that sense. And then what I'm now hoping that by applying more of the pluri-subharmonic calibrated theory, we would sort of recover some bits of quadratic analysis which never existed, because people usually try to do this theater type hyperholomorphic functions in quadratic analysis, and they never have any geometric applications. And these ones obviously do. Okay. Now, why do we need this? The point is that we need to discover what is a Kähler cone. So what I will be telling you today, this construction of moduli space, most of it was actually known in the 90s and even earlier. So the mapping class group is due to essentially to, well, it's mid-90s at the computation of Teichmüller space could be done again in the 90s and even earlier if we had a description of a Kähler cone. And in fact, it would suffice if you understand the Kähler curve from generic deformation. And for generic deformation, it's actually very easy, except that it's hard to prove. The cone is very easy, and it was obvious to anybody that it is just the biggest possible space. Okay, so what is a Kähler cone? Definition. A Kähler class is a class of Kähler form, and Kähler cone is a union of all Kähler classes. And this notion was studied by Kodaira and Spencer, and Kodaira proved that, in fact, well, it's not hard to see that the Kähler cone is open. So claim Kähler cone is open in H11 of M, which sits inside H2 of M by Hodge decomposition. So the question was, is it possible to determine the Kähler cone for any manifold at all? If we do that, we sort of have much control on the algebraic geometry of the space of complex structures. Okay, and there's this beautiful theorem of Demey-Pound, which allows to determine the Kähler cone. So claim theorem. That says that if consider the space K inside H11 of M, which is the space of all two forms, which are integrated positively over all Z. Of course, if a form is scalar, you can integrate it over a cycle and obtain something positive, but the opposite is true. So Kähler cone is a connected component of this set K. Now, for a general hyperkähler manifold, we understand its cycles, complex subvarieties, because they are all trianalytic. And for trianalytic subvarieties, this number is easy to compute, as you will see just from topology of the subvariety. So this brings an answer about the Kähler cone. So corollary, Kähler cone of a general hyperkähler manifold is quadratic, in the sense which I will explain very soon. And the original work on that direction, I wanted to tell that this theorem of Demey-Pound was obtained by this duality argument of Harvey-Lawson. It's not true, unfortunately. I double-checked. So, but the original work done by Hilbert was precisely using this other paper, this one. So it's actually a very interesting paper because it's essentially the only theorem which you can prove about non-Kähler manifolds is here. So what it says is that if you have a manifold which is non-Kähler, it will necessarily have a positive current in n-1, n-1 type, which is part of something closed. Anyway, if you do this long enough, you will obtain beautiful results like a theorem of Lamary. And it actually it's quite similar to this hyperkähler theorem, in idea at least, and the theorem of Bousdal-Lamary, of course. So it's Bousdal-Lamary, not opposite way. And it says that if M is complex surface, then B1 of M is even if and only if M is scalar. So if you work with non-Kähler geometry, I think this is the only way you... This work about duality, which uses Han-Banach type theorem, is the only way you can obtain some new, well, so far, new results. But this was this theorem was different. Though the original, it's actually quite funny because the original argument, which was obtained using the duality, was wrong, and it seems it's hard to do correct mathematics using this duality, and this was why it was almost never cited, though I think it's one of them. Well, at least I read it several times through and gave some courses on it, and still it remains a favorite piece of mathematics. Okay, sorry. So let me continue with this hyperkähler stuff. Now I will tell you something about the topology of hyperkähler manifolds, and for that you should add some restrictions. If you want to work with differential geometry, these restrictions, which I'm adding, it's just restrictions on holonomy. So you want the hyperkähler manifold to have trivial holonomy, well, maximal holonomy possible, without any reductions. So the definition, yes. Yeah, it will be also, you can compute it, of course. Thank you. Yes. Please excuse me, it was, I should have started from that probably, but it would be too special. So M is simple if holonomy of M is SPn, and which is equivalent to what is written there, which is, and equivalently P1 of M is trivial, and H20 of M is C. This equivalence is due to Bogomolov, I think, and he actually proved the version of Berger decomposition for Calabi-Yau manifolds without using Calabi-Yau. It was earlier result. So what he did is he looked at the complex manifolds, scalar manifolds with trivial canonical bundle, and he proved that they can be decomposed onto the simple pieces, and he defined the simple pieces in terms of the cohomology. And this equivalence was actually added later when the Yau proved Calabi-Yau theorem. Okay, so now I will always assume that without, I should have actually assumed this earlier. But there is many topological results about the simple hyperkähler manifolds, and for today I will state some of them. And the simplest, well, not simplest, the most powerful topological result is the following. So if you have, it's a result about automorphism group of the cohomology. So if G is automorphisms of cohomology ring, there is an obvious map from G to GL of H2 of MR. And this theorem claims that there exists, but know the image. So the image, we have a subgroup. Did I denote it somehow? No, I didn't, so I can do it right now. So we have G0 sitting there, and this G0 is spin B2 minus 3, 3. And it projects there in obvious manner, because this is, you can think of this spin of B2 minus 3, 3 as a group of automorphisms of H2. H2 has the same dimension as B2, so it works. Well, and you can say something more about the group of the automorphic cohomology. For instance, you can prove that it's the kernel of this map is compact. It's not hard. Anyway, so we know the automorphism group. And as you see, this image is actually some symmetric group. I mean, it's a group which is orthogonal with respect to some metric. So this sort of suggests that a metric must exist, and this is true. Actually, the metric was obtained earlier than this automorphism result. And there is this result about metric. It is, of course, you can write down the metric as I did in the formula. It doesn't help much, but on the other hand, one can define it using the, and you see this very big formula in the middle of the slide. It was actually the original definition. And the Fujiki theorem obtained later, and this result obtained even later. But it is very interesting because every time, if you work on some topological manifold, you have a map, cup product map, H2 of M, if it's even dimensional, mapping to H top of M, just eta goes to integral of, well, it's two numbers, to integral of eta power p over M. You see, it is p-dimensional polynomial map. It's a polynomial of degree p, but what does Fujiki say is that for M hyperkähler, this cup product map is a top power, well, nth power of a quadratic polynomial. It's very special. And so when essentially this was sort of discovered by Bogomolov, but he couldn't believe it, and he published a proof that hyperkähler manifolds don't exist, essentially, except K3 surface. And unfortunately, it was published in a Soviet journal which never refereed. So nobody pointed out an error to him until Fujiki constructed a counterexample by doing the Hilbert scheme of 2 points on K3. So, but still it is very strange and beautiful topological result, which allows, of course, to work with the hyperkähler manifolds very efficiently. And when I was speaking of this Kähler cone on this, well, on the general manifold, I meant precisely this quadratic cone. So the Kähler cone of a general hyperkähler manifold is a cone defined by this form in H11. In H11, it has signature by, if you look carefully on this, what is it there, you will see that in H11, this quadratic form has signature 1 at B2 minus 3. So its cone has two components. It's usual quadratic cone like in Lorentz space. And you take one of these two components, obtaining the Kähler cone of a hyperkähler manifold. Okay. Now, after I told you about topology, let me tell you about the mapping class group. And its computation is entirely topological. I mean, what do we need to compute it? We are interested in the quotient of diffeomorphism group by isotopies. And in fact, it was computed long ago by Sullivan in this paper, Infinitesimal Methods in Topology in Publication of HS. It has bits in the end where he uses the formality of the So what he does generally is he computes this mapping class group in terms of rational cohomology, of rational homotopy of a manifold. But then we know that for a Kähler or hyperkähler manifold, the rational homotopies are sort of trivial, they are formal. And this allows you to express this mapping class group in terms of automorphisms of the algebra of cohomology instead of the homotopy type, rational homotopy type, which is much harder to understand. So for general Kähler manifold, you should this is needed for topology, for Smale's theorem on H-cobordism. If you have a Kähler manifold of good dimension, then this projection from the mapping class group to automorphism of cohomology has finite kernel, and its image has finite index in automorphisms of cohomology. Here, by automorphism of cohomology, I mean the automorphism of integer cohomology preserving the Pantagin classes. Good. And as you see, we have this theorem here. It's easy to see that this group, which I just constructed, preserves the Pantagin classes. It follows from Fujiki formula. So we have we have a map from the mapping class group to automorphisms of this H2 with Fujiki form, and it has finite kernel and finite index. This is, allows you to express the mapping class group in terms of the just automorphisms of one lattice. And this is very good because it's what is called arithmetic group. Arithmetic group is one which is commensurable to algebraically group over integers. And in our case, it's not only arithmetic, but it's arithmetic subgroup in a simply group. So you can apply lots of results about ergodic theories and so on, obtaining many interesting theorems about mapping class group. Okay. This was the part about mapping class group topological, which I have how much? Good. Now we will explain the algebraic geometric part, which is a bit harder because it's the answers are harder, and mostly because it's the moduli space is extremely non-Hausdorff. So you need to do something with this non-Hausdorffness to obtain effective results. But fortunately, we have a very powerful tool. Well, Hodge theory is essentially this tool. So, but in that case, it is called Bogomolov's or Bogomolov-Tian-Todorov theorem, which says that the locally deformation of a hyperkähler manifold is uniquely determined by its periods. So what do I mean? Let M be a hyperkähler manifold. As I told you at the beginning, we have this, we assume it is simple, right? I think I erased that, but we assume that. This means that H20 of M is C. Of course, this H20 is a line which is determined by the complex structure. This gives you a map, especially if we think that you have already fixed the basis in H2, which we can do that because we are working on Teichmüller space. So I have a map from Teichmüller space to a projectivization of H2 of MC. Mapping a complex structure I on M into the corresponding line H20 of Mi. This is a period map. And the good thing about the period map is that it is locally injective, and in fact, you can determine its image very easily. So let's define the period space of M as the subset in the projectivization of the H2. So it's the set of L inside predictization of H2 MC such that L times L is equal 0. Here I'm using this Puchik's form, and also Q of L bar is positive. And I can put several slides. There is this properties of this signature of this form, which immediately imply, if you think of it, that the period map lends you into this period space. And of course, this is a nice space. It's homogeneous. If you look at it, the corresponding automorphism group, which is our O of H2, acts homogeneously, transitively on this space. So you can describe the space in different terms by using some very simple, it's like first year linear algebra or second year, which can be used to express this period space as some homogeneous space as follows. So it is SO of B2 minus 3 quotient by SO of 3 times SO of 2, sorry, times SO of B2 minus 3, 1. Okay. And yeah, this period map is a tal. So the map, let me state it. That if you have the map from Teichmüller to period space is a tal. A tal meaning that it is locally diffeomorphism, of course. It's just algebraic geometric way of expressing local diffeomorphisms. Okay, so this is, of course, it's very much non-Hausdorff. It's easy to see that it is non-Hausdorff even for a K3, in fact. So there's no way to deal with non-Hausdorffness of the whole thing. But in fact, there is a way of dealing with non-Hausdorff of Teichmüller, and let me explain how it is done. Okay, so let's just start with some very basic general topology words about the manifold. So you can define, I mean, half textbook assume that all manifolds are Hausdorff, and there is another half which define non-Hausdorff a manifold as topological space locally diffeomorphic or homeomorphic to Rn. It's not clear topological, well, locally homeomorphic to Rn. And then you add, on top of it, you add Hausdorffness. But you don't need it. I mean, if we forget about it, we immediately obtain that this Teichmüller space is a manifold, which is good. So we do that. We define non-Hausdorff manifold, and we say that it is the Teichmüller space is non-Hausdorff manifold, and then you can understand what are non-Hausdorff points. So first, the points are non-separable if you don't have, if there is no open neighborhood separating these 2 points. This is this tilde relation which I define on this line. It's obvious. I mean, the typical problems with non-Hausdorffness come from this kind of double points in real line, for instance. And these are 2 points which are non-separate. And the very beautiful theorem by Hilbert says that if you have 2 non-Hausdorff points, the corresponding varieties are birational equivalent. This means that you can blow down some divisors, blow up, and you obtain one variety from another. Obviously, it's actually, the converse is sort of easy. If you have at least it's obvious that if you have two varieties which are birational equivalent, they correspond to the same points and periods. This was actually example obtained by Hilbert, who first observed that Torelli theorem that was originally understood as a statement about Hodge structures is false for hyperkähler manifolds. It's false because you can have two hyperkähler manifolds which are bimeromorphically equivalent, and they have the same periods, and by Hilbert's they actually correspond to the non-separable points in the moduli space. Well, we can do that. We can start just generally from a non-Hausdorff manifold, define this relation, and try to take the quotient. This would be sort of, you can do that even functorially, and it would be sort of the biggest, if you have a functor from embedding from Hausdorff manifolds to non-Hausdorff manifold, you can try to construct the adjoint functor. And if this space would exist, it would be an adjoint functor, which you could call Hausdorff quotient, but it doesn't. So typically, this tilde is not equivalence, the quotient is non-Hausdorff, and so on. This is a problem. Fortunately, this problem can be resolved very easily if you work with period space. For period space, there is this notion of weakly Hausdorff manifold. You can define it axiomatically, or you can work with periods, doesn't matter. But if you want to define it axiomatically, you do as follows. Weakly Hausdorff manifold is a manifold where first all non-Hausdorff points sits on divisors, or just on any real index subvarieties of dimension 2, or on subvarieties on subsets of Hausdorff dimension, codimension 2. This is enough. There's nothing. Real index is not really used in the proof. The only thing is used is that it has Hausdorff codimension 2. It's for topological reasons. We want that locally the complement to this set of non-separable points is connected. And on top of that, so we want the set of non-Hausdorff points to be very small, and on top of that, we want to have a period map. This is just what we need from a period map to state the result. We need it to be surjective, continuous, to a closed ball on Rn, and to induce homomorphism on any open neighborhood. Then it is called weakly Hausdorff manifold. So you have these two conditions. This period map obviously satisfies S, because this is it. I mean, this period space is smooth, and you have the period map to something smooth, which obviously locally at the homomorphism. And non-Hausdorff points of Teichmüller are obtained in countable union of divisors by a Hilbert's result. Because what does he say is that if you have two non-Hausdorff points, you blow up a divisor, you blow down a divisor, blow up a divisor, but existence of a divisor is a codimension 1 condition in algebraic geometry. So this means that the non-Hausdorff points are actually rare. They exist only on the divisors. Okay, so we have now this period space, the period map satisfying it. How the Teichmüller space satisfies the whole thing, and you have a theorem that weakly Hausdorff manifold admits a Hausdorff reduction. This means that you can state it against categorically as that if you have a map from embedding of categories from Hausdorff manifolds to weakly Hausdorff, and this Hausdorff reduction is adjoint functor. Anyway, the point is that the quotient is Hausdorff, and this map is locally a homomorphism. The map from X to its quotient. You glue together, it's like in this calculus example with lines with 2 points. If you have lines with 2 points, you can glue them together, obtaining a usual line. Okay, so this gives us some control over the non-Hausdorff points of the Teichmüller space. And the quotient is called birational Teichmüller space. This is not technically precise because it doesn't classify, well, you glue together some birational points, but it is a nice space. Anyway, so now the theorem, which is one of the main theorems, at least a theorem which explains the geometry of the Teichmüller space, it says that it is an isomorphism. It is a theorem about the map from Teichmüller to period space. So how you proved such a result? Well, it's not hard. I mean, what we have is we have our hyperkähler structures. With each hyperkähler structure, you can associate the twistor space, like Nigel explained just an hour ago. And this gives you a deformation of your hyperkähler manifold over a CP1. And since the hyperkähler structures are in one-to-one correspondence with Kähler structures, and Kähler structures are determined by the Kähler cone, we have an explicit understanding of how many these CP1s sit inside that period space. Now the idea is to prove that the period map is a covering, because we know that the period space is simply connected. It's this space. You can check by using first-year topology to check that this is simply connected. So if you prove that this period map is a covering, you are done. And to prove that it is a covering, you just check that it is a covering on CP1s, and then you check that there are enough CP1s for the covering to be checked only on CP1s, and this is doable. Of course. Well, now then, we don't want really Teichmüller's theorem. I mean, Teichmüller is okay, but what people usually want, they want a classification of hyperkähler manifolds, not up to some mapping class group, but real classification. So we can define the moduli space. And the moduli space by taking the periods, the birational moduli space, it's a quotient of this birational Teichmüller space by the mapping class group. This is a space which classifies the complex structures up to birational equivalence, but not quite. The point is that we have glued together some of the non-equivalent points, which are birational equivalent, and then we take a quotient. Anyway, this quotient is again non-Hausdorff, and it is non-Hausdorff in a very bad way. If you apply these ergodic type arguments, which I tried to explain earlier, you will see that there's just no non-Hausdorff points there. So all points are sort of infinitesimally, the distance of the metric on a quotient is 0. The natural metric, I mean this quotient metric. So it's the quotient, the birational moduli space is a very bad variety. But if you try to think of it as a stack, it's okay. Anyway, so we know what it is now. It is a quotient of the period space by an arithmetic subgroup. And of course, typically people don't want this. They want the global Torelli theorem is a statement about Hodge structures. For K3 it works. So the Hodge structure, which is this line, it determines the complex structure. For K3, for curve, well, for curve it's not a line, but still it's a Hodge structure. And but unfortunately it's typically false. So let me explain how it is false. There is, you can ask for birational Hodge-theoretic Torelli theorem, which is what people conjectured in, I think you can find this conjecture in Hilbert's paper in 2000, but then there were found counterexamples. So this is the best conjecture in 2000 because it sort of avoids the debar counterexamples. It says that, you see there's this definition, but what is essentially it says that deformation of M up to bimeromorphic equivalence is determined by the Hodge structure. This is what we have for K3, for instance, for curve, for abelian variety, for many other complex questions, complex manifolds. Anyway, but there's a problem. The problem is actually not, of course, Markman did this very beautifully, but there was earlier counterexample by Nemikava, who found that, in fact, he found a general and very beautiful construction of other hyperkähler manifold, two hyperkähler structures with the same periods on what is called generalized Kummer. Anyway, Markman just computed that. He computed the mapping class group, and he proved that it is a subgroup generated by oriented reflections. It's an implicit computation, which allows you to immediately to check whether two different complex structures, two different points in periods, satisfies isomorphic or birational isomorphic subvarieties, and he found the counterexamples. Just for most of the Hilbert scheme of K3, it's false. So this is a theorem. Suppose you have a Hilbert scheme of K3 where it's p plus 1 points. Like 3 points is okay, 4 points is okay, 5 is not okay. And then the usual global Torelli theorem, Hodge-theoretic, holds birationally to deformation of Hilbert scheme with isomorphic Hodge structures are bimeromorphic, and for other it is false due to that result. And this is, I think I have finished. Thank you very much. And happy birthday to Blaine. It was a very nice conference. And also, yeah, I wish to thank the organizers. It was such a pleasure to be there.
Okay, are there any questions about the talk?
And you know that all fibers like except 0 are hyperkähler.
Yes.
Inside the central kähler is also hyperkähler.
If it is kähler, it is hyperkähler. But there are examples when it is not kähler.
I do not assume the central kähler is kähler.
Yeah. If it's not kähler, there are counterexamples. It could be moisture zone, for instance. There are moisture zone varieties, even diffeomorphic to a hyperkähler manifold, but not kähler. So you cannot degenerate a variety to something moisture zone. It's easy. You take a hyperkähler manifold with two P2s, and you do Mukai flop on one P2, and the other remains the same. You'll obtain a manifold which is diffeomorphic to the original one, but it has two curves which have opposite orientation. So if you sum them up, you obtain something which there's no classes in H2 which you can integrate over this curve positively. In fact, the sum in cohomology is 0, I think, in that particular example. It is something that known, I think, maybe to the bar. Cranese told me this example. I didn't see it published, but it seems to be well known.
How to prove subjectivity of that?
You just take a point, and you take CP1 going from this point. Then you take, since you know you can start from a general point. And you know that there are lots of CP1s because they're controlled by the Kähler cone, and you know what is a Kähler cone. Then you take another point, and you do the same. And you take a third point, you do the same. After these three operations, it implies surjectivity immediately. It was known actually to Hilbert already that you can do that. Of course, yeah. So every 2 points are connected by CP1s corresponding to hyperkähler structures. Every 2 points in periods, because there are lots of CP1s which are parameterized by Kähler cones.
So you call the modular space bad, but people in the dynamics actually love the spaces because it is the beginning of ergodic theory. So do you have any interesting ergodic questions and answers about the action of the lateral Teichmüller space?
Yes, there's a lot. In fact, what we did recently was that take a divisor which corresponds just to a plane here, in fact, if you look. And then the quotient, in the quotient it is dense. So every divisor, giving you some algebraic family, is dense in the moduli space. And recently there was a question which is due to, well, it is a question of suppose we have a closed subset here such that it intersects every CP1 by at least one point. Every CP1 which comes from three-dimensional subspaces in this space. And it is invariant under the group action. Will it be the whole thing? It is similar to what to this Klein box type ergodic theorems of, but so far it is not known. If it is true, then you can prove that every hyperkähler manifold is Kobayashi non-hyperbolic. So it has applications for algebraic geometry. And there are more of them, of course. You can ask and ask billions of questions. None of them are answered, unfortunately.
Perhaps, yeah. So I just wanted to very briefly express my gratitude. Thank you for a beautiful lecture, by the way. It's a nice segue into the next meeting, which starts tomorrow. Hyperkähler geometry. But it's been a wonderful meeting, and I really wanted to express my gratitude to the people who organized it and ran it. None of them, unfortunately, are here. For the record, if this is being taped, Mike Anderson, who did so much work in organizing the speakers and so forth, and then Lucille Easy and Lynn Barnett, who, as you have all seen, have done a tremendous amount of work in making this run as smoothly as it has. Really indebted to them. And I'm also indebted to all of you who went to such trouble to come here and to give such beautiful talks. I thought it was going to be a painful time going to all these lectures. In fact,